afternoon, everyone. Let's jump right into our last topic. Applications. And we're, for the most part, with one exception, we're going to be using what's sometimes called the general population model. In most of the questions, you're going to be given this formula, but I want to show you what the general version is and where the pieces come from. So the population P of some town, say, or animals, whatever you like, is given by the formula P equals P naught, e to the power of RT. P naught is the initial population. And naught is an old word for zero. Did you know that? Naught is an old word for zero. So it's been here for a while. So what did the population of the town start with? R is called the growth rate, written as a decimal, and T is time. Let me show you a question that would have that. Let's suppose that we had a town, and in this town, it started off with 200 people, and its growth rate was 2%. So the growth rate is 2%, is where that 0.02 came from, and it started with 200 people. So maybe it was one of those Western stories where a wagon train with 200 people stopped somewhere in America and said, yep, this is where we're going to do our thing. This is where we're going to build our town and grow our families. So you got this one. There are two distinct types of question that you're now going to get with these formulas. And the first question is the easier of the two, and that is, what will the population be? And then insert some number like 6 years. And the second kind of question is a kind of how long question. How long before the population of this town becomes, oh, I don't know, let's say, I wonder how long it takes the population of this town to become 500 people. That's the two main types of question you're going to get for the majority of the questions. You've got a formula, population model formula, and it asks you, what will the population be in 5 years, 10 years, 6 years? And you're going to use this formula to do that. And the second question is, how long before the population reaches 500, 1,000? Sometimes they phrase it like, how long before the population doubles, which is just another way of saying 400. So let's look at each question in turn. Question 1 then. If you want to know what the population is like in 6 years, you're essentially just going to calculate that guy. Right, so it's a plug-in, Chuck. So you have to kind of know where the buttons are in your calculator to do that. So I've got this one here, and it's 200. So I guess I could write this down since it is more like notes. 200 times. And there are two different ways to get the E. I'm going to use the button. So blue button divide. So second divide. That gets you the E guy. So blue button divide. You see the E? Then you do power. Just that button. And we've got these two guys. I like to put brackets around things to be safe. So I do a little bracket. And then I do 0.02 times 6, and then I can close the brackets. So 0.02 times 6, and then I can close the brackets. And then you finish with enter. And you're going to get, in this case, 225.4 and lots of weird decimals. Since these questions are typically people or things, it's normally the case that you round it off to the nearest whole number. So in this little story, the town started with 200 people in it. The growth rate is 2%, which isn't very high. And in 6 years, they've grown to, well, a reasonable number, right? 225 people. So it has grown a lot. Is there anything about the plug and chug? This line here is just telling you what buttons to press on your calculator. Are we cool with this type of question? Because it typically is the easier of the two. Let's do another one of those. And let's, well, I guess I'll call it 1 again. That can be called 1A then, and this is 1B. Let's suppose that the second version was how many people in 60 years? So the population is going to be 200 e to the 0.02 times 60. Would you expect, I think I would anyway, a lot more people? Agreed? If you 60 years of growth, it's just going to be a lot more people. So 200 e to the power, put in a bracket, 0.02 times 60. And this place has grown to 664 people to the nearest whole number. So this town is probably never going to turn into Seattle. Would you agree it's growing really, really slowly? I mean, even after 60 years, it's only just slightly more than trebled its size. So it's now 600 people. Now, I said there's two kinds of questions. Let's show you the second one. Question 2. How long before the population, say, becomes 500? Now, those type of questions are a little bit tricky. You start off with your formula. But now you know the population. In this case, it's going to be 500. And what we're going to do is solve for t. We are going to solve an equation. It's an exponential equation because it's got e to the power in it. And as long as you do it to both sides, it's okay roll. But we have to kind of make sure that we do things in the correct order. What would you say would be the first thing I should do to both sides here?
Could you divide by 200?
That's exactly what you should have done, yes. You nailed it. Since this is notes, I'm putting in the calculation first. Now, in these population model questions, you're eventually going to get a line that looks like this, right? 2.5 equals e to the power or whatever it is. And at this point, we're going to use a guy that I had a nickname for called the Circle of Life. Can you remember the Circle of Life guy? And what that's going to do is it's going to turn this exponential into its logarithmic form. So you start with the base, go there, and then you finish here. So what does that look like? Well, it looks like the log to the base e of 2.5 equals 0.02 t. Right? The log to the base e of 2.5 equals a power. Are we okay with that guy? If I look at my calculator, with the exception of Sarah's, who's got a fancy one, you will not see a log to the base e button. But the log to the base e is one of these buttons. Can you remember which one it is? Is it the button they call log, or is it the button they call ln? Which one is that guy?
ln, the natural log.
Right. So I can now Write that down. Don't worry about what that is. That'll be a calculator button pressing thing later on. Let's just finish off the line. I've got a number, because that's what that's going to eventually be, equals 0.02 t. What do I do to both sides to find t?
Would
So
you
this
divide
number-
again 0.02?
You do. And I kind of wait till I've got to this stage, and then I use my calculator. So it's going to be the natural log of 2.5 divided by 0.02, and the answer that I get is about 45.8. And since this is years, I'm just doing it to one decimal place. Maybe the WebAssign wants 2, maybe they want a whole number, but it's about almost 46 years. So if this town wanted to get to a size of 500, can you see it would have to, you know, be a whole generation of people would have to pass, right, before that happened. Are we good? So let's create another one of these, and I'll do a couple of questions with it, and then we'll start looking at their ones. Right, here is a model that is representing an epidemic. The amount of people who have the disease is given by this formula. Now, in the story, you started with 20 people with the Scottish flu. The growth rate is 51%, which as a decimal is 0.51. And I'm going to have time in days, because time doesn't always have to be years, right? In fact, see, when you do bacteria, time can sometimes be minutes. Right, the little buggers grow that quickly. You know, time can be in minutes. And so for this model of an epidemic of Scottish flu, 20 people come over from Scotland with the flu and they give it to Americans. And we are now going to see how many people will have the flu after a certain amount of time. So the two questions we're going to have is question 1, which is how many people will have the Scottish flu after, say, a month, after 30 days. Before we get the answer to this, do you think the answer is going to be in hundreds or in thousands? What's your gut feeling? Hundreds or in thousands? What do you think it's going to be?
Thousands.
Most epidemics are, aren't they? They just go through the roof really quick. That would be my gut feeling as well. So A is 20, E to the 0.51 t. The time gets replaced by 30. And since this is people, I'm going to round my answer off to the nearest whole number. So it's 20 multiplied by E to the power of, put a bracket in, 0.51 times 30, close the brackets, and 882542337. Well, actually 8. Was that a surprise? 88 million Americans have caught the flu, the Scottish flu. I mean, it is in thousands, But really, I should have gave you the choice of millions. I never thought about that as an option. Amazing.
I
At
wasn't
that
expecting it to be that high, but
Neither was I. But the numbers don't lie. If the infection rate, which is essentially what that's called, is very high, then an epidemic can shoot through the roof before you know it. In other words, you know, half the population of America. In fact, based on that number, if that was true, it wouldn't take actually that long, would it, before everybody in America had caught the flu. Right? But thank goodness we haven't got an epidemic yet that is that virulent. Right? Even COVID, didn't COVID take months, not days, to reach that kind of number, right? So we know that most epidemics do have a much smaller infection rate, which is thank goodness. Now, second question then is a how long to? So how long before? Let's just have it as 1 million. How long before 1 million people have this? You start off with the formula. You put 1 million here. Now, if you remember how we solved the last one, this is going to be virtually the same process, right? Same steps, each step pretty much the same, right? Divide both sides by 20. So I'll do 1 million. And I'll divide it by 20. And I get 50,000, I believe. Now, once I do that, we'll do the little circle of life thing, right? Wasn't that the next step? So log to the base E of 50,000 equals the power. Okay, what shall I do to both sides now?
Turn it into the natural log.
Actually, I should have asked that question first, so you are right. What do I do now to find T?
Divide by 0.51.
And on my calculator then, the natural log of 50,000 divided by 0.51 comes out to be about 21 days. Now, thankfully, this is a totally made up story, but can you imagine there was such a thing as Scottish flu? Can you see that if it was as virulent as this darn flu is, there'd probably be, you wouldn't be able to stop it. Would you agree that it would explode into the population quicker than you could quarantine or do anything? It'd just be, it would be a bad place to be. So let's just hope that the next COVID thing, whatever that's going to be, isn't that bad. Are you comfortable with this question? Do you get the feel of how these population growth model questions work? You're given a formula, you plug some in to get how many people or how many things, and then how long before something. Kind of looking for visual clues. I see a lot of writing, but not a lot of nodding. Okay, I got some nods. Right, well, you know what I'm going to do? I'm going to give you one to try, because if I do that, I'll feel comfortable about it. Then I'll show you a population decline model, and then I'll show you a log model, and that's, apart from showing you some homework questions, that's us. So here is your question. What will we have? A or B? What that one? A or B? Let me see if I can. isolate a question here. Yeah, let's do a P.
Can I ask a question, please, Professor?
Yes. What is it, Nadia?
Why did you write that it is 21 days?
The right answer I got was 21.21, and I just decided to round it off the whole number.
Ah, because it was like in a condition of this question, right?
Yes.
Uh,
You know, you have to read the question to find out what they want. Sometimes they want nearest whole number. Sometimes questions want 2 decimal places, whatever the question would ask them. Right. So let's have a population model
okay, thank you.
where you start off with 3,500 people. And the growth rate is 4%. So just looking at that, I can tell you that you start with 3,500, right? And looking at that decimal, I can tell you that the growth rate is 4%. Basically, that means that the population grows by 4% each year. So here are your 2 questions to try out on this one. The first one is, what's the population going to be in 10 years? And the second question is, how long before there's 100,000 people living in this? Well, it'll be a city by then. So, what's the population going to be in 10 years? And how long before there's 100,000? I'll give you 5 minutes to show, well, 4.5 minutes actually, to get that one done. If I keep this one here, it's a very good template for doing this one.
I'm sorry, Professor, I have a question, please.
Yeah, go for it.
I cannot find that button for E sign.
Okay, let me show you where it is. You're using a calculator quite like this one?
It is TI 84 plus.
Yeah, same inside. Right. On the top left, you've got a blue button or a second button. It might not be blue in color.
Uh-huh.
And do you see the division button, which is like below the
Oh,
clear
yeah,
and the
yeah,
power?
you told I just forgot. Yeah,
So
yeah.
blue button, that guy.
Okay.
That's where it's hidden.
Right. Thank you very much.
You've got 1 more minute. Let's work on this fella. In 10 years, all I basically did is plug 10 in here. So it's 3,500 times blue button divide, that's e to the power. Put a bracket in, 0.04 times 10. And we'll just assume that we want the answer to a whole number since it's people. I got a population of about 5,221. Right. Looks good. Okay. Now, the second question is how long before this place has 100,000 people in it? So how long before it becomes a city, I guess. So this number is 100,000. And the formula basically gets rewritten again without any changes. And just like we did before, to solve this exponential equation, we go through very similar steps. Can't say something often enough. What do I do to both sides? Next.
Divide
Divide by
by
3,500.
That's what I heard from virtually two people almost in unison. So I know that you were both going to say the same thing, right? Agreed? And which I'll now turn into some horrible decimal. So here goes 100,000 divided by 3,500. And I get about 28.57. You may have rounded it off a little bit differently, but I don't think we'll disagree too much, right? So what is next then? What's my next line going to look like?
Divide by, oh wait, no, yeah, now you have to do the log E, right?
Yeah,
Move the E over.
log E of what number?
Of the 28, it's the 28, right?
Yeah, 28.57.
2857. And then you have left is the 0.04t.
Right,
I
you
meant
do
to answer
my-
the next
yeah.
part, not that part.
So yeah, you do the circle of life, as I call it, right? I just think it's
Circle of
easy to
life.
give some a name, right? Because if you try and describe what you just said, although it makes sense, isn't it kind of wordy? So if you just say, I do the circle of life, we all kind of know what you're doing, right? But what you said is perfectly correct. So this becomes the natural log. Though after a while, you probably don't need this line, right? Because you know where that button is on your calculator. And to finish then, we divide by 0.04. And I have no idea what this is going to be. I might get surprised again. 28.57 divided by 0.04. And the answer we get is what, about rounding off about 84 years? 83 point something if you were more accurate than I was. Does that look about right? But if you think of the practicalities of this, 3,500 turning into a city of 100,000 only takes, what, 84 years? Right. That's like the lifespan of one person, right? You could have been a baby when the town was founded, and by the time he gets to well into his retiring age, it's grown to 100,000. That does not happen very often. Would you agree if that happened in every town, wouldn't America be billions rather than hundreds of millions, right? It's quite interesting when you look at the history of America, why some places got big and other places are like 200 or 300 and really didn't change much, that in fact might even decline. Is there any particular reason why some places just shoot off and become Seattle and other places, just hang around at the same kind of number and don't grow much at all?
Opportunities for trade.
It's just financial? If you're in the right place at the right time, boom.
There's
you're
a
up and
reason why
running.
most of them are on the coast. They had harbors.
Right. So the beginning of the growth of America is based on selling stuff to other people, and sending it by sea meant being on the coast was a good place.
Can I ask a question, please?
Sure, Naja, what?
My calculator shows that the number is 83.80.
I like your answer, that's what I got.
Do we,
And
well, what, do we leave it like that, or do we have to round it for a whole number?
The question will tell you. So I just decided unilaterally whole numbers, right?
Yeah, just
And
a
when I'm
quick-
looking at a question right now, and the question I've got here says to the nearest foot. So if the question says to the nearest whole number, 84. If it says to 1 decimal place, you will write 83.8. If it says 2 decimal places, 83.81, right? So the question will tell you what you need to round off to. You don't need to be so, well, should I make it a whole number or not? Whatever the question tells you to do.
Okay, thank you very much. I have another question, please.
Go for it.
How do we make a difference between, for example, in one question, there was a condition for days, and then this, it was for years. How do we make difference? We just read attentively a question, or how do we figure out?
I didn't sorry, I didn't catch some of the words there. So you were asking how do we tell the difference between two types of questions?
Yes.
So what was your first question again? What was the key to that?
One question, number one, that you have on your left side, it has days. And this one, as far as I understand, it has years, right?
Yes, that's in the question.
So again, in a question, we're reading.
Yeah. So the question will say, here's a population model, T is in days. Here's a different model, T is in weeks or years. It typically depends on the story, whether T is in days or years.
I think what she's asking is because before it was really important that we convert everything to years, but on this, you're saying we don't need to worry about any conversions. Was that what you were asking, Nadia?
Yeah, that's right.
Well
Okay,
done.
yeah.
I didn't pick that up, Tara. I got what you mean. Yeah.
No, you're good, because I was
the-
wondering the same thing. I just was doing what you said, but
Yeah,
she had a really good question.
Yes, very good question. Yeah, whatever the question happens to say, if it says days, then don't change it. If it says, I mean, in bacteria questions, time could even be in hours. Right? So if it is in hours, then, 14 is 14 hours. So far, so good?
Yeah.
Right. So next fella is essentially the same question, but this is a population growth model. What happens when instead of something increasing, getting bigger, right, a growth model, the population actually declines? And what does that look like? Well, it looks like this fella. So what's the difference? The growth rate will be a negative number. So if the R value is a negative number, it's not actually a growth rate anymore. What's in fact happening is the population is going to go down. So imagine we've got a town in the Midwest, and this town has 550 people in it. But it's not a prosperous town. Actually, people are leaving more than, the growth is. And you're losing 2% a year. So time is in years again. And these are very often called, rather than population growth models, these are very often called population decay models. It just means things are decaying, going down. And that's actually quite realistic. Aren't there some places in America that are just dying out, right? Some towns are just, not able to keep their population, and each year there's a few less, right? Let's find out what happens. Well, you get exactly the same two questions. The two types of questions are, how many people will live in this town after, say, 15 years have gone by? And the second question is, how long before the population becomes, say, 230 people? So I guess this is a model that represents places turning into ghost towns. Is that what you call them in America? Ghost towns? That term's coming out my head anyway. Eventually, if things keep going, don't you end up with nobody lives in the town or a couple of people live in the town, and when they die, you know, that's the end of it. Right. The good news is that we already know how to do these questions. So let's do one. It's 550 e to the negative 0.02t.
370.
And we want 15 years. So 550 e to the negative 0.02 times 50. Now, there's a little hiccup that you have to be careful on using your calculator here. So let's show you what the buttons would be. 550 times e to the power bracket. Now, that negative is where the mistake can happen. And it's happened in other calculations as well. There's a guy here that looks like a negative, he's in grey. And there's a guy down at the bottom that looks like a negative, and it's white. But only one of those two is actually the correct button. Which button do I use? The white one or the grey one? Which represents? Yeah. You ever done the wrong one and it says syntax error? So if you hit the wrong button, you kind of know because it'll say that. So white button, 0.02 times 50, close the brackets, and 202 people. I'm rounding it off to the whole number again. So it didn't take that long, right? You started off with 550 people. And in 15 years, it's going to be, what, 202. Can you imagine another 15 years, it's almost gone, right? So the
Wait,
second question,
Professor,
yes.
in
Yes,
your
yeah.
original question, you asked how many people would be in this community after 15 years.
Oh, let's change the question to 50 years out. That way I can keep, the answer. Okay, it took a bit longer, but it's still on the way out, isn't it? Probably another 50 years will probably kill this place. Right. Now, how long before the population becomes 230? I'll keep that one. So we begin with the formula, but in question 2, we know that the population is 230, and we're trying to find what t is. It's very, very similar, isn't it, to the questions we've done today. We are going to solve. It's almost carbon copy. There's one minor little difference, and it's really quite minor. So let's just start the process. What do I do to both sides?
Divide 500 or 550.
Okay.
Oh, no wonder my numbers were wrong. I wrote 500.
And 230 divided by 550 is about roughly 0.4182 if you round it off. Can you see the circle of life happening? Right. The next line. Can I just write down that line? Is it okay for me to skip the log to the base E line and then just write it down as Ln? You know, one less thing to write down. Are you okay with that?
Is that a trick question?
No,
Okay, good, because I was
you
already
are
doing.
okay with that. You are okay with it, yes?
Yes.
You know, some people just don't like missing lines, so I'm just putting that out there. Right, what's the last thing I need to do then to find T? What do I do to both sides to find T?
Divide the 0.02.
Negative.
Yes, with a negative, but I'm assuming you knew that, so. Okay, hit button time. The natural log of 0.4182 gets divided by negative 0.02, and notice I used the negative button. And the answer I get is about 43, and just to be awkward, I'm going to do it to 1 decimal place. So it takes about 43.6 years. So we'll assume that the question said to 1 decimal place, and this question said to nearest whole number. I am going to show you an application of that that's kind of cool. If I can just wait a second, I'll actually show you me looking for it. That might be interesting. I'll get a chat question, should anyone I know about. Okay, gotcha. Now, let's show you what the heck's going on. Is it this one? Are you looking at your Math 107 Canvas site?
Yes, indeed.
Okay, now I'm going to click on this and I am going to look for what's called carbon 14 dating. Has anybody ever heard of that term?
I've heard of carbon dating, but not carbon 14.
That's just specific. Carbon 14 is carbon dating. It just happens to be the isotope of carbon that they use, right? So I guess I'll try this one. What I'm going to look for in one of these is the model, the formula that is used to date things using carbon 14. Now, if they don't give me the number I want, I know how to get that number, but I'd rather they just told me what it was. Blah, blah, blah. Okay, 5730. And nope, that didn't work. Okay. Maybe I should put in carbon 14 model. That might work. There you give me. I'll get pretty pictures. There's the isotope. Let's check that one maybe. No, I did not want to buy a ThinkPad. That is annoying. I know that its half-life is 5730. That doesn't really help me any, unfortunately. Okay. We are going to create the formula for the half-life of carbon 14 then. And they've got a thing called the half-life. If you've ever done, I think it's in chemistry, it's about 5,700 years. Right, let me just return. I was just hoping to find a site that gave me the formula and we could just use it. So the first part of what I'm going to do today, you don't need to even write notes on. It's just me creating the formula. It might be interesting because you just want to know how the formula came about. The half-life of a radioactive material is the time it takes for it to change from what it is into a new isotope. And basically, all radioactive material have half-lives. Right? Has any of you ever done chemistry and they've talked about half-lives? Right, Tara, what did they say about it? What can you remember they tell you about it?
Half-life, I can't remember the formula. I was trying to rack my brain there for a second.
Don't worry about it.
Of it, but basically the half-life of it is where it becomes, for what we're doing for chemistry, it's when it no longer is harmful. So at this point, at full life, a chemical is harmful, but at its half-life, most chemicals are no longer harmful to us. So
Okay, so
knowing how to calculate is important.
We gotcha. Right, so I am the first person, pretend I am the first person in the world, and I want to create one of these models, right? One of these guys here for carbon-14. So what I would do is I'd say, right, I know the general form of this model. I'm going to assume that I start with 100 grams of carbon-14, and I know that its formula is that.
Can I ask a question, please?
Yes, Nadja.
Are we gonna have to use this formula in our exam?
This one, no, but these ones, yes. And these questions, the formula will be given to you in the question. So you do not need to create the formula.
Yeah, but we don't need this carbon-14, right? Or half-life.
Once I figure out what the number is, we will use the question, but you will see it written like this. Right. So it takes 5,700 years for you to get half of it. They have just told me that he is half of this guy, so it's 50. And they have told me that it takes 5,700 years for that to happen. So I now have an equation which I'm going to solve. I will divide both sides by 100. I will then do the circle of life. I will then divide both sides by 5,700. And what I have now done is found what I was hoping to get online, which is what is the decay rate for carbon-14? And they tend to be ridiculously ugly small negative numbers. So here goes. The natural log of 0.5 divided by 5,700. And that guy there is just a calculator being a pain in the butt. It's really saying that. Okay, I now have the formula that I want. So pretend that never happened. The amount of carbon-14 is given by 100 e to the negative 0.0000121 t. So pretend that was the start of the question. We can use carbon-14, right, to tell how old something is. What you do is that, you know, archaeologists have discovered this, that if you find some organic material, like a piece of wood that was left in a fire, right, or a piece of the wooden shaft of some sort, you can actually tell how old the object is. And what happened is that normal carbon, the ones that we typically have in our bodies, isn't particularly radioactive, but there's an isotope of it called carbon-14. And this particular isotope is how you judge the age of something. You find out what percentage is still left in that piece of wood. So 100% is brand new, right? So if I went and cut down a tree and I took a piece of wood off that tree, right? Its carbon 14 would be 100%. In other words, it has the normal quota. And then time goes by. And let's say that we get a piece of wood and it's only got 57% of its carbon 14. I can tell you how old that piece of wood is, right? So what they do is they take the piece of wood, they put it in a machine called a mass spectrometer, and the mass spectrometer does its clever stuff. But what it does is it pops out a number and it says it's got 57% of carbon 14, right? It should have 100%, but it's lost some. Divide both sides by 100. Circle of life. And divide both sides by that really ugly decimal. And that fictitious piece of wood is 0.57 divided by negative 0.000121. And it ends up being 4,646 years old. So if you've ever seen programs on TV, archaeologists, and they're digging up some, buried ruin of a town or maybe a native community's village, and they turn up and they say, we've done some carbon 14 dating, and this particular village was being inhabited 4,646 years ago. And you think, how on earth does anybody know that from a little piece of wood? Isn't it kind of amazing what you can do when you have a formula that uses a particular isotope of carbon and how much of that carbon is still around? You can actually do that with all sorts of things. Human beings have carbon 14 in them. Tara, you've got carbon 14 right now. You ate it this morning when you had your lettuce sandwich or whatever, right? So, not that you're going to, but if suddenly all of Bremerton was hit by a volcano and we all get buried alive, dead, whatever, and 10,000 years from now they dug it up, they'd be able to tell how old Tara was when she died. So it's kind of cool. Before they had carbon 14 dating, a lot of archaeology was intelligent guesswork. If they found something, they would try and judge how old it was by the style of it, right? Pottery had a certain style in one age and then it changed to another age. But it was very hit and miss. And I do remember a really interesting article I read where when carbon 14 was first discovered and being used, a lot of museums went back to their exhibits and did the ones that they could do, they did carbon 14 dating on them. And in some museums, they had a failure rate of 60%. In other words, they said this wooden shaft was 4,000 years old and it was actually 6,000 years old, or it was 2,000 years old, right? They got the dates really wrong. And you can't blame them, right? One moldy piece of wood looks kind of like any other moldy piece of wood, right? You don't really, it's not that easy to judge age. But it was a fascinating thing. I thought that was fascinating. So if you use this formula, can't you use it to find the age of anything? The carbon 14 dating one. I don't think I need to give you a question on that because it's really just the same as the other ones, right? So our last question, and then we'll look at the homework, and that's pretty much everything that we've done, is the only example of a log question. It's the only one I think I've got. And it's question 5 from the homework. And log of capital E is 11.8 plus 1.5 m. And E is energy that you get from an earthquake. And I did not know this until I picked this question. Do you know that the energy in an earthquake is measured in a unit called ergs? I've never heard of it, but evidently energy from earthquakes are measured in ergs. Earthquakes are phenomenal, like major ones, right? Biggies. They are phenomenally powerful. Can't a really decent sized earthquake split the San Andreas? I mean, it splits the earth open, right? It is massively powerful. So do not be surprised when this number ends up being extremely large. And the thing that's called M is a guy that I have heard. Have you heard of the Richter scale when they talk about earthquakes?
Oh, yeah.
Anybody who, yeah. You were going to say something, Kayla?
Oh no, I just hear that all the time, especially in primary school when we learned all about the big one we're supposed to have.
Oh, the big one that hasn't happened yet, big one?
Yeah, that's the one.
But you know the big one will happen when everybody thinks it's not going to happen.
Yeah, yep, they also said that.
Okay. I don't want it to happen either. I'm quite happy if it takes 2,000 years for it to happen. I'm quite willing to wait that. Well, I won't be here, but the Richter scale is a very interesting scale because it's not, if you know a little bit about it, it's not the kind of scale that you would expect. It's a number, right? It goes 1, 2, 3, 4, and I don't know what it goes up to. Let's say it's up to an earthquake 8 or something ridiculously big. The scale is what's called a logarithmic scale. Now, what that means is that an earthquake of level 1 and an earthquake of level 2, an earthquake of a Richter scale 2 is not twice as, powerful. It's actually 10 times as powerful. And a 2 to a 3 is 10 times powerful. But a level 3 earthquake is 100 times more powerful than a level 1 earthquake. So you can see that the units go up in scales of times 10s, right? Which is not the usual kind of linear scale, right? So a 3 and a 6 are not double each other, right? A 3 and a 6 is 100 times more powerful. So you don't want to be in a level 8 earthquake. You don't want to be anywhere near one of those. In fact, if one of those happens by the sea, won't the tsunami probably kill a lot more people than the earthquake will? I mean, earthquakes make buildings fall down, but if you're out in the open and nothing hits you, you're probably going to make it, right? You don't want to be by the sea if there's a tsunami that gets caused by one of these. So which number do you want an earthquake for? Yeah, well, Karen is going to go for a level 1 earthquake, right? That's the kind of earthquake that makes your table shake, right? Even if that, right? But after that one, then we're going to do a second and final one where we're going to do the 8.3 that flattened San Francisco, right? The last biggie, I think it was, right? So we are going to see how much energy is in a level 1 earthquake, and then we're going to find out how much is on an 8.3, which was the San Francisco one of 1906. So the log of E is 11.8 plus, make sure I get my decimal point in. That's a decimal point there, and it's a decimal point there. 1.5 m. And we're going to do a level 1 earthquake. So that's number 1 on the Richter scale. So that's 11.8 plus 1.5 times 1 And that ends up being 11.8, add 1.5, that's 13.8. So far, so good. Now, have you noticed that this log does not have a number base written beside it? Can you remember what base you assume when you don't see a number?
Isn't it 10?
It is. So can I just add in the 10, even although it's not there? We know it's there, you just won't write it. Now, the reason I'm doing that is that we need to find out what E is, right? So the question is, on a Richter scale of 1, how many ergs of energy would that take, right, to cause a number 1 earthquake? Which is a pretty minor earthquake, right? It's a wobbly earthquake. Can you remember the circle of life? Let's do it. Start with the base. Go to
Professor,
there. Yes.
wouldn't it equal 13.3 instead of 13.8?
Did you all catch that deliberate mistake? Does anybody here even believe it was a deliberate mistake? Right. Okay. 10 to the power of this, thank you for catching that, equals A. So 10 to the power of 13.3 is equal to E. And that is a scarily big number. It's 10 to the power of 13.3. And look what that isn't even actually the number, it's got an E at the 13 at the end. It's about 2 with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. X. The good news is that you just write your answer like that. A level 1 earthquake will do 20 trillion ergs of energy. It's scarily big. Now, what's the only difference going to be with a 1906 8.3? Oh, here it is. The log to the base 10 of E is 11.8 plus 1.5 M. It's going to be 11.8 plus a 1.5, and the earthquake was an 8.3. 11.8 add 1.5 times 8.3, and we get 24.25. And the circle of life, what do we get? 10 to the power of 24.25 equals E. And very roughly, right? Very, very roughly, it's 1,000 million, right? 1,000 million ergs. I mean, isn't that kind of American debt size? That is, you know, a phenomenal number. And I think we are pretty much finished all of that. So I am going to go and do something that has just got my interest, hopefully yours. And I'm going to type in Richter scale. And see what we got. Okay, I'll zoom out and in, and hopefully you'll get to see this thing. This is a nice little graphic to show you what a Richter scale looks like kind of in layman's terms. So the one that you were wanting doesn't even qualify on this picture. Anything of a 2.5 or less, you usually don't feel it. But one of those little pen things, you know, the things you see the wiggle of the pen and it zooms up and down on the paper, and that would recognize it. Anything between 2.5 and 5.4 is often felt, but only causes minor damage. Has anybody here been in an earthquake? Tara, where was yours? Well, we'll do Tara and Aubrey next. What did your earthquake look like, Tara? Where were you
It
and
was
what did
super weird. I was in Issaquah at the time. My 22-year-old daughter was a baby, so it would have been quite a while ago. We were right by the train tracks, and you could see, I think they said it was like a 3 something magnitude that hit. You could see the train tracks moving, and everything on our walls came down, and it was right, and it was pretty wild. Like, there wasn't a lot of damage to everything, but it was just weird to look at the train tracks because they were straight, and they weren't straight when it came through.
So basically, after that, they had to come and relay the track, I'm assuming.
Yeah, they came out and did some work. It was one of those ones that was just in the old area of Issaquah that they didn't use for any actual, they didn't use it for anything. It was just more of a tourist attraction. So, but yeah, it was very weird to see it like galloping.
Aubrey, what was your experience? I think it was Aubrey. Who else?
Yeah, it was me.
What did you get?
I was in 2019 around, was it, I don't remember, but around 2019, summertime or so.
Where were
In
you?
Christmas, I was in both. There was an earthquake in the Philippines. It was a 6.8, I believe,
Ooh, okay.
magnitude. I was in a restaurant, and then I was the first one to notice it because I could hear my keys for the car shaking in the water. And then we got out of the building, and the moment I stood, I was tipping, and then I saw the cars moving.
That's kind
Like
of
this,
scary.
parked cars. Yeah,
'Cause,
it lasted for about 27 seconds or so, and then after, like, because I get car sick, I usually get car sick, I had a headache.
Not a surprise. According to this, that's in the strong range. May cause major damage. Very often, it depends on how well built the buildings are.
Mhm.
So if you're in some places where the quality of building isn't great, buildings can fall down. So it was a good idea to get out of the restaurant in case it was a poorly built building. But that was a 6 point. Anybody else got a earthquake story? You been in an earthquake?
I felt one. There was one a few years ago. I was just laying in my room, and it was weird because I like felt everything shake.
Mm-hmm.
I thought like a piece of furniture or fallen or something,
Right.
so I just went to sleep, and I didn't find out the next day that it was an earthquake.
Your story is very like mine. I have only been in one earthquake. We don't get earthquakes in Scotland. At least you don't get ones that you can even feel. And I was in Alaska, and I was in our house, and my wife was sitting down, and we were watching TV, and I was standing up by the kitchen getting a glass of something. And I felt this shudder, like I thought someone had like maybe banged the chair. It wasn't bad, but I felt this sound kind of feeling a little movement, and I thought, oh, did somebody bang, a table or something? And I didn't find out the next day that it had been an earthquake. So if you're really far away from it, you probably have had an earthquake experience, but you never even knew it was one. That was my earthquake experience. Totally uninspiring, right? I thought someone had banged a table and it was an earthquake. Not much of a story, but that was my experience. I don't want to be in a big earthquake anyway. I'm quite happy for the big one not to come. But since I'm in stories, I'll tell you another one that just came to me. When I lived in Alaska, everybody in Ketchikan, Alaska has a bear story. Something to do with bears. I don't have a bear story. I lived there and never never blinking saw one. I think they were, I don't know, they just hid from me. But my brother-in-law has got a great bear story. He lived in not that, I mean, pretty central part of Ketchikan, and he was taking the garbage out, and you take the garbage, and you always keep your garbage inside. You don't leave it outside because the bears like garbage, so you don't want to encourage them. And so he was walking down, and he has a big set of stairs, and then in the bottom he has a kind of garage, and he keeps the garbage in the dustbin in the garage. And he'd opened the door, and he'd close the door, and he'd put his garbage into the bin. And then he turns round, and he saw the silhouette of the bear walking by the door that he just came in. And he didn't move or do anything except push things against the door. And he waited about half an hour, and then he opened the door and had a quick peek, and then shot up the stairs. So that was his bear story. He was that close to meeting a bear personally. I don't think I'd want that either. Anybody got a bear story?
I do.
What you got?
I lived in Georgia, and we have black bears in the mountains, and it was pretty common to just have bears go through the trash like you're saying. And one of my uncles, he's not like very I don't know, he didn't really know about, like, you know, he's the kind of person that feeds bread to ducks, you know what I mean? So he would just feed this bear marshmallows, and this bear just loved him. It was the ridiculous thing. But they had somebody come down and I think like trap the bear and transport it somewhere because it became such a problem. But I don't know. I just remember watching. Well, I watched him feed the bear marshmallows from the window because his wife would babysit me. But I don't know. I guess they really like marshmallows.
Yes,
So that's my story.
Well, they connected to what you just said. What they do in Ketchikan is that they don't like bears to be in the village, right? For pretty obvious reasons. There's kids around, right? You don't want bears getting comfortable with people. And so, yeah, everybody keeps their garbage inside, as we said. But if they have a bear and it hangs around, they will catch it, like you said. And what they do is they pick that bear up and they tag it on its ear, I think, and they pick it up by a helicopter and they fly it to the middle of the island, and then they let them go. But they have a rule: if they catch a bear that's got a tag on its ear, they euthanize it. It gets killed. Because if it returns a second time, it's just not safe anymore.
Yeah, that makes sense.
So that's what they do. I mean, it must cost a lot of money, because you can
Yeah,
imagine.
I would think so.
They don't put it in the helicopter, in case you were wondering. They put it in a basket underneath the helicopter, and they lift it, and they drop the basket, and I guess they have an opening mechanism, and the thing gets out and runs away. But that's what they do. And
we had one like your brother's thing where we put the trash. We had a shed. We used to put the trash in to take it, and a bear got in there. My mom told us to fill up balloons with ammonia and put peanut butter on them. First of all, do you know how hard it is to get ammonia into a balloon? It is not
I've never
fun.
tried, but I'll take your word for it.
I go through all of this to put ammonia in balloons and put peanut butter on them because I want this bear to leave, and I have little kids, and go out there the next day and the bear is eating the trash. The dog is eating the trash with the bear, and they did not care about the ammonia or the peanut butter balloons. That was my horrible experience. Then he just never came back after that.
Well, he probably ate the ammonia with the peanuts and then figured out that your garbage wasn't worth it. That's maybe what happened. You know, he probably put the word out, don't go to that house. Their garbage tastes really funny. So, well, let's just finish this off, and then I'll show you a few bits and pieces, and then we'll talk about what's coming in the future. Right. That 8.6, was it? Yeah, the 8.3 is the great earthquake, and it can totally destroy anything that's near. So San Francisco got pretty much flattened into it in 1906. but they rebuilt it, which makes you think, why would you rebuild on a place that's a earthquake fault line? Are you just an optimist or kind of dumb? Wouldn't they? My experience would be if an earthquake flattened the city, maybe you shouldn't build there anymore. Make it a national park and build somewhere else.
If California did that, there would be a lot of people with nowhere to go. I don't think they can help it. It's too nice there. They've decided they'll brave it.
They'll risk it. I
Yep.
got you. Well, that's pretty much it. So let's close off this window. This window. Closing off a lot of windows here. Here we go. So I'll make this a little bit bigger. And I'll show you what I've got. Stop this. And go back in again. Right, with a bit of luck, are you all looking at 107's canvas thing? Okay.
Yes.
You may already notice this. Have you noticed I've got a thing called practice final exam? Have you seen that? That's a new thing. Now, if you click on it, and I do that, are you looking at practice final exam with solutions? Okay. So what I've got here is just a resource. It's not homework. It's not extra credit. It's just something that you might want to use as part of your revision for your final exam. Because we've just actually finished. There's nothing new to be done, right? You've learned everything you're going to get. This is like your final, but much bigger. So that's the first piece of information. Your final exam won't be as large as this practice. Your final exam will have 10 multiple choice and 10 section 2s. Right? 10 multiple choice worth 10 points each, that's 100 points, and 10 section 2 questions worth another 200 points. So here is an example of the types of questions that I like to use in multiple choice. Now, this guy, Peter, has 3 banks, and he can do a compounded monthly, a compounded weekly, or a compounded daily. And one of these 4 is the best one, right? So if you wanted to put your money in the bank, you would choose one of these banks over the other 2. Now, one of the things about multiple choice questions is, if it takes you more than 5 minutes to do it, you're doing it wrong. So some of you might say, oh yeah, I know there's a formula for annual yield, and I'll go and look up that formula and I'll write it down and I'll plug in the numbers and I'll do it 3 times, and one of them's going to be bigger than the other 2, and that's my answer. Well, you would get the answer eventually. It would take you more than 5 minutes, right? But you would get the answer eventually. What is the right answer? And you should be able to do it just looking. A, bank 1, bank 2, or bank 3? Which is the best?
Bank 3.
3. Why? You're correct. Why is it 3? Because not
Because-
everybody answered that, so maybe they're not so sure. Why is it 3 better?
Because it's compounded daily, so it's compounded more often than the others.
And that, as long as the percentage stays the same, isn't that going to make the difference? So if you see that question, it was pretty easy to answer. You would just say C. So what's going to happen in the final is that all I will get from you from section 1 is 1 is C. I don't want to see working, because in the multiple choice, you either give me the right answer or you don't. So you either get all 10 points or you get none at all. So certainly there will be working for some questions, but I don't want to see it. All I will get is essentially the answers, right? 1 is A, 2 is C. Now, what are you going to do in a multiple choice if you don't know the answer? Do you leave it blank or do you pick a letter? What do you do if you don't know an answer?
Pick any answer, the one you think is the most right, because you have a 1 in 4 chance of getting it right. So
Use probability. Yeah, 1 in 4 chance. What do you do if you think 2 answers are right? A and B are both right. What do you do when that happens?
Choose the one that feels the most accurate.
Okay, pick the one that feels more right. Okay, multiple choices can only have one correct answer. The fact that you think that there is 2 isn't helpful. You have to commit to one. You can't say A or B because I will have to give you 0 points. Pick A, great. Pick B, great. But pick only one. Right, so if you're not sure of multiple choices, always guess if you don't know. And if you think it's 2 answers, flip a coin in the air and pick whatever heads is A and tails is B, whatever you decide. And if you're in the military, don't you always guess C when you don't know? Allegedly. And here are basically a whole load of questions, probability questions. There's a dice question. Here's one, question 20. What's the standard deviation of data 3, 3, 3, 3, and 3? Now, I could actually do that in my calculator, and it probably would take less than 5 minutes, so that's fine. But what is the answer without doing any of those calculations? What's the standard deviation if all the numbers in the data set are the same number?
I think it's B, right?
Yes, it's 0. Correct. What? Isn't standard deviation measuring how much variation, how much spread there is in the data? There isn't any, so it's 0. So you should be able to do that question if it happens relatively quickly. Double-blind experiment. You heard of double-blind? Let's remind you. That's when the people don't know what treatment they're getting and the doctor doesn't know who's getting it either. And the reason we do it, it's the best method to make sure you get good data. And it keeps on going. Oh, there's a box plot. There's some log calculations. And here's just it's not really a homework, it's not really a final question, but I like to throw things in sometimes just to get you thinking. If P is true and Q is false, what is P or Q? And you pick one of those. I wouldn't worry about that. Now you get to section 2. And in section 2, I do expect you to show working. And there's going to be 10 questions in section 2. And here we go. And here are the answers to the multiple choice. And here is the working and the answers. In section 2. A couple of strategies that might help you. This is what I've found has helped a lot of students over the time. Time management is very important. You have 3 hours to do your final, which does feel like a lot, and it is a lot. Most of you, if you do it efficiently, will not need 3 hours. But when you're finished, you have to take pictures and then upload it into Canvas the way you always would. And there's going to be a Zoom meeting, just like we did in the midterm. So that's not going to change. But when you come to do section 2, I suggest strongly you do the following things. Read over all 10 questions first. Now you don't need to read them, in depth, but read over them to see what they're about. And the reason why I'm asking you to do that is that once you've done that, you should be able to break the 10 questions into 3 main groups. The first group are the good ones. Aren't there going to be some questions that you've done tons of them and you can do them in your sleep? And the good ones you do first. Do all the questions you say, yeah, oh, we just finished doing that population model one. I'm really good at them. Give me a calculator, 5 minutes from now, I'll be finished. Then that should be one of the questions you do first, even although it's probably going to be question 10, because my tests are in chronological order. In other words, the last thing we did is question 10, the first thing is week 1, right? Then the second group, these are the ones that you let's call it sort of a know. You know, the kind of questions where you're pretty sure you know how to do them, but you know, sometimes you start it and then you get lost a little bit. And you do them next. And then the third group. What the heck is he asking there? I've never seen this question before. Well, maybe I've seen it before, but I've forgotten what it's all about. I don't know what he's talking about. I'm lost. And you always do those guys last. So I'll give you a little pretend story why this is a good order. Now, this could simply be, let's talk about it. It could be that you end up doing the questions in a really weird order. Right, I'll do questions 9 and 10, 7 and 4. And then I'll do 5 and 6, and then I'll finish with 1, 3, 8, you know, that kind of order. As long as you do your questions on single pieces of paper, it's going to be fine. Because once you're finished, can't you put them in order and take pictures of them? So I won't not really care. But the main reason why I want you to do these is, can you imagine that you're doing the test and question 1 on section 2 is a horrible question. You don't know what the heck to do. If you think you should do the questions number 1, then number 2, then number 3, then number 4, that could easily happen that early on you get a stinker for you. What happens, I found has happened, is that students who get that, they spend 20 minutes stressing out about it, and then they try something and it doesn't work, and they put big cross through it, and they try another version and it takes another 10 minutes and it's just as bad as the first version. Half an hour has gone by and you haven't answered one question. Now, aren't you now in the wrong frame of mind for the rest of the questions? Right, you're already stressing yourself to the point where you don't need to be. On the other hand, see if you do all the good questions first, won't you hopefully be able to say to yourself, hey, I've probably already passed. You know, I'm not too worried now. All I'm doing now is, I don't want a 2.0, I want a 3.0. So that's what I'm fighting for now. And that's a much better mindset to be in. So think about, seriously, think about reading over section 2 and picking the easy ones first, the so-so ones second, and the stinkers last. Any questions about the final? Just general questions.
Professor, I have a question. Could you
Yes.
please repeat one more time? We have to make photos of both sections or the second only?
Let's show you what you're going to do. In section 1, that's the multiple choice.
Yeah.
All I'm going to see, all you're going to take a photograph of will be a page that looks something like this. 1 is A, 2 is B, 3 is C, 4 is D, you know, and so on. So all I will see is something that looks like that.
So we do
I
it
will not see
manually.
working at all, right?
We do it manually. We don't make it, write it in a WebAssign, is it right?
Correct. It's not going to be in WebAssign. It's going to be in a PDF.
Mm-hmm.
So all you're going to do is write them down, and that's good. Now, section 2 is different. On section 2, you are going to show me question 1 and all the working. Question 2 and all the working. Question 3 and all the working. And in section 2, you get partial credit. That's one of the reasons I want to see the working. And in question 2, you get, if you get like 3/4 of it right, you'll get 3/4 of the points. Does that make a little bit more sense? Is that clearer?
Do we have to write down question itself? I mean, conditions?
No. All you need to do is tell me it's question 1 and I know what question 1 is. So you don't need to write the question again. That takes up too much time.